Okay, so good morning and welcome to our last CGD seminar of 2022. Just a note, we will resume seminars in person, online actually, on January 6th of next year. So our first one in the new year will be a Zoom seminar. Just as a note. So it's my pleasure to introduce today's speaker, Nicholas Lybarger of NCAR's Research Applications Lab. So Nick was recently promoted to a project scientist working in the hydrology section of RAL in June of 2022. Nice. So Nicholas holds a PhD in climate dynamics from George Mason University in Virginia and a bachelor's in physics and earth and planetary science from the Johns Hopkins University. So prior to his position as a project scientist, Nick was a postdoctoral researcher at NCAR in RAL in the Joint Numerical Testbed Division. He was working with a group that interrogated the current generation of physics suites in the Unified Forecast System framework, where he was particularly investigating the track error seen in the system for Hurricane Barry, which hit the Louisiana coast in 2019, July 2019. And was utilizing the storm as a way of identifying ways to improve the physics suites for ongoing development of UFS. So Nicholas's PhD work, he developed a statistical model relating to the Madden-Julian oscillation to El Nino, and published multiple papers on that, including revisiting MJO, Kelvin waves, and the El Nino relationships using a simple ocean model, and MJO, wind energy and prediction of El Nino. So Nicholas will now present to us on improving our methodologies of selecting Earth system models for climate change impact applications. And as a quick reminder, if you are watching online and you'd like to ask a question at the end of Nicholas's presentation, to please go to our Slido page. And if you just go to slido.com, you can find the page. It's #CGD seminar. And you can enter your question there, and I will read it out after Nick is done presenting. So, to you.
All right. Can everyone hear me okay? All right. So yeah, I'm Nick Lybarger. I work over at RAL, at the Hydrometeorological Applications Program. I'd like to thank Monica and CGD for hosting me, and also the U.S. Army Corps of Engineers, who are the primary funders of this project. So today I'm going to talk about improving our methodologies of selecting Earth system models for climate change impact applications, particularly with a focus on hydrological impacts and a particular focus over the Pacific Northwest on this particular project. So this is part of a three-part project that we're funded for. The idea is to, at every level, have selection criteria to inform which models and which methods we're using to project hydrological changes in the future climate. So the work I'm presenting today will be focused on the top level here, the ESM scenario selection, where I try to create a flexible framework for evaluating ESM processes to be able to apply to any region, basically. And then from there, once we have a set of ESMs that we believe are reliable for a particular region, we will then apply downscaling methods on those ESMs using downscaling methods that we determine to be reliable through another project I'm working on. And then from there, we'll take that downscaled data and apply it to hydrological models in order to assess what climate change scenarios might look like from a hydrological perspective using the best DSMs and the best downscaling methods, whatever that means. So yeah, that's the context of this project. And we're still characterizing uncertainties, but the idea is to reduce those uncertainties by assessing and applying these methods only to those models that are the most reliable. And determining that is the focus of this study. So the motivation is that projecting climate change reliably is a difficult problem, obviously, and requires a very large amount of data, and this has only become more true in the era of CMIP6. And policymakers are interested in knowing which models are the most reliable, and if we can reduce the number of models to be considered, in order to reduce their computational load when they want to do some sort of climate change impact study. So the objectives here are to assess and scrutinize the methods of reducing the ensemble size for stakeholders that may have limited time or computational resources, and then determine, basically, using our metric suite, which models have the best representation of processes relevant, specifically in this project, to the Pacific Northwest water availability, and then to generalize that framework to be applicable to anywhere in the world, basically, where you have observations to verify anyway. So in February 2021, before I joined the group, there was a workshop, an expert workshop, where they invited ESM developers, climate change impacts scientists, and water resource managers from the U.S. Army Corps of Engineers and the U.S. Bureau of Reclamation. And they determined that points of emphasis are as listed here. There needs to be deeper information sharing between model developers and users to understand process deficiencies. We need to focus on diversity of model response rather than just diversity on model genealogy, and using more metrics from science fields and at scales not often applied for water resource applications, including global scale metrics, which is something that's still ongoing, but is we have some results for. And then a specific emphasis on improving the evaluation of ESM representation of the forced climate change response, both globally and regionally where possible. So the methods I'm going to employ today, or that I've completed, I intend to show that I've developed a suite of metrics that include process-based analysis of features that are relevant to the Pacific Northwest, and that's for CMIP6 historical runs. I'll then rank the models according to their performance relative to observational data sets, which I'll present in a second. And then from there to cull the models according to this metric using simulated historical precipitation and temperature trends as a secondary criteria in addition to the metric suite. So then I will then analyze how the projected future precipitation and temperature trend envelopes are affected by this process in various shared socioeconomic pathway runs of those CMIP6 models. And then perform split sample analysis to check the reliability of the culling criteria, where I separate the models, the data, into two different sets, one from 1901 to 1950, and the other from 1950 to 2014, as a way to verify this culling criteria. And then, yeah, so here's the metric suite we're using here. Most of the metrics I'm showing today are from the highest confidence category of the Rupp et al. 2013 paper, and their analysis of the P&W in the CMIP5 simulations, including mean annual precipitation and temperature, the seasonal amplitude of precipitation and temperature, the annual trend of precipitation and temperature, and then the seasonal spatial correlation and seasonal spatial standard deviation of precipitation and temperature. And then in addition to those, there are 6 other metrics that I'm going to use to evaluate the representation of El Nino within the model, using the newly developed ELI index, that is INSO longitude index, developed by Christina Petricula in her paper in 2020, as well as the more traditional Nino 3.4 index. So that includes the bias of the median DJF ELI, Levine statistic for DJF ELI, which essentially investigates how the distribution of ELI matches that of the observations, and then the spatial correlation between the modeled temporal correlation maps for Nino 3.4 and ELI with temperature and precipitation. And then global metrics are computed and will be included soon. I have some results to show based on the global metrics. And then we intend to include other metrics in future work, including oceanic heat content or other emergent constraints from the literature in the future. So the data I'm using are 57 CMIP6 models acquired from the CGD archives, which were in turn acquired from the ESGF database. This list is intended to be as comprehensive as is reasonable. Only a few models were left out due to various technical issues, such as unclear documentation, inconsistencies between ensemble members, or prohibitively unconventional grids. So we're including 6 different precipitation and temperature gridded observations for verification. That is the CREW precipitation and temperature data set, ERA5 reanalysis, GMET data set, which is intended to be some representation of the observational uncertainty, and then the University of Delaware precipitation and temperature, LIVNA, and the PRISM precipitation and temperature. For the precipitation and temperature trend verification, I only use the CREW and University of Delaware data sets because they have the longest temporal coverage going back all the way to 1900. And as you can see, there's actually errors on this slide. The CREW, UDEL, and ERA5 data sets are all global. So those are used for the global verification that I'm going to show at the end as well. And the results I'm going to show are also specifically for the Pacific Northwest, a region defined there from 30 to 50 north and 135 to 95 east. And for all these metrics, the models and the observations are regridded to a common 1 degree by 1 degree grid. So here is a busy slide full of all the different metrics results and showing the distribution of the CMIP6 historical runs about those observations. The observations are shown by the cyan circles here. And what we find is that the models in the Pacific Northwest tend to be a bit too cool and wet, but trends are a bit too warm and dry. And we find that temperature trends are generally better represented than the precipitation trends, and that the ELI, which I should describe a little bit more, I'm not sure if everyone's familiar with it. The ELI is the INSO longitude index. It's been shown in the literature to better represent INSO diversity than the traditional Nino 3.4. So the idea is that one would expect models that represent ELI better would represent INSO diversity better, and when it comes to things like precipitation impacts in the western United States, Eastern Pacific El Niños tend to have a much stronger influence on precipitation than do Central Pacific El Niños. So representing that process better should be represented in the ELI. So we do find that the ELI tends to be poorly represented in CMIP6, suggesting that INSO diversity is not well represented either. We see a strong eastward bias in essentially every CMIP6 model. And that's shown in this ELI median bias here. This is the target. This is, if there was no bias at all, we'd be right on this line. So every model shows an eastward bias to varying degree, which means that the El Niños in the CMIP6 models are primarily of the Eastern Pacific variety, and there's not much representation of Central Pacific El Niños. Yeah, but in general, here's the spatial correlation by season of temperature and precipitation, and the spatial standard deviation, which, you know, you can stare at this all day and find interesting little features, but the idea, I mean, that's the metric suite that we're showing here. So then I ranked those models according to the relative error of each of those metrics. And here we have the high performers on the left and the lower performers on the right. And the ensemble spread is represented by the colored dots about each ensemble mean error in the large black dots. So what's interesting to me is that you tend to see little plateaus besides the edges. I mean, at the edges, there's some pretty big jumps between the different models. But you get into these plateaus where, like right here, all these models perform very similarly, and then there's a little jump. All these models perform pretty similarly, a little jump, and then another plateau, another plateau. And something that I want to investigate that I haven't done yet is what are the similarities between these models that tend to clump together, whether it be physics, cumulus parameterization, whatever. It would be interesting to determine the characteristics common to those models. Or if there's not characteristics common to those models, that would be interesting too, because it means it's just a coincidence that they happen to be grouped together. So here is a lot of information, but that's the full CMIP6 model suite that we're looking at here. And I want to focus, some of the information's been lost here. That's okay. Over on the top left here, these are our top performers. And you can see that there are, the ensemble size varies greatly between these. Basically, I took whatever was available at the time. And the SSP 245, SSP 370, and SSP 585 are what I'm looking at here. So if you look at the ranking based on 1901 to 2014, here is each of those models ranking. It's ordered that way. And then for the split sample analysis, if you consider the metric suite but only look at 1901 to 1950, you can see that this ranking is pretty stable. I mean, you see this one and this one, I've highlighted in red because they drop out of the top 16 and are replaced by these two when you consider the split sample analysis. But in general, like the top 10 models are very stable, and it doesn't change that much. It lends credence to the robustness of our results that the split sample analysis tends to produce a very similar model suite. And I'll show some more results from the split sample analysis in a moment. Yeah, there were some bolded black lines on this table that showed some interesting things, but they're not there, so what are you gonna do? So here is the effect of culling on the historical trends. So if you look at the top left here, the idea is that when you order models based on their metric performance, you add, as you move down the x-axis here, you add a model to the suite each time. And so you get to a point where the error between, so the observations are the dotted lines here, the observational average. So we tend to see models that are, that the trends are too dry and the observations are much wetter than what we see in the CMIP6 models. And the temperature trends tend to be too warm. The observational average is right around 0. Oh no, never mind, I'm sorry, I was reading that wrong. The observational trend for temperature is around 0.55. Then we tend to see that the models are higher than that. So the idea is you get to a point where you reach the minimal error between the temperature lines here and the precipitation lines here. So that line for the historical period is 21 models. So you see the minimal error between the trends for 21 models, and that's how we objectively determine the criteria for our culling threshold. And if you look at, so this is the same plot, except you only consider models that are included in the SSP suites. So not every model has a corresponding SSP suite. The historical model list is much larger than the SSP list. So if you consider only models that are included in the SSP 245 envelope, you get an optimal envelope size of 13, the minimum error here. If you consider SSP 3.7, you get an optimal envelope size of 11 and 14 if you consider 585. So these are all still the historical trends. It's just a different model suite included, depending on which are included in the SSP runs. Yes?
I'm sorry, just wondering, so the minimum error here just means that you have precipitation trend and minimum error for both. So you're picking out whichever that's the smallest.
Right, yes.
But the process of culling here, is it when you're
Well, so if you go all the way to the right is the predicted trend, or the historical trend for the entire model suite, which is 57 models. Over on the left, those numbers on the very far left of the x-axis, it's only one model included in that.
And you're adding one model based on.
Right, yes. Yep, as you move to the right, you add one model, yep. So here are the CMIP6 scenario trends for every model that can be included in each suite. So the historical trends include all 57 CMIP6 models that we consider, and then the SSP runs have smaller suites of 42, 41, and 45 models. And this is what the projections show us is going to be the case. And so I'm going to show how these envelopes change based on our culling criteria. And as predicted, the 585 is warmer, and it also happens to be wetter, and that's true. Basically, these behave as expected based on how they're defined. And so the effective culling on the projection envelope, over here on the left, we have the change in the historical trend. So the black bars are including all 57 models in the CMIP6 suite. And the cold set of that optimal number of 21 models is shown here. And we see that the precipitation trend becomes slightly wetter, which is closer to what we see in the observations, and slightly cooler, which tends to make it lie more toward the center of these projected temperature trends from the Crew and University of Delaware data sets. And so here we have the change in the projected trend based on the optimal culling from that model envelope. So this includes the black bars again include all models, and the red bars and dots are only including the cold models. So the idea is that there are small changes in the projected mean and standard deviation, but there's perhaps smaller changes than you might expect. You cull out most of the extreme models, and what you're left with is a distribution that includes much fewer members, but still represents the uncertainty and mean of the full data set. So if the goal is to reduce the amount of data you need to consider to get a full picture of what the projection envelope looks like, then I'd say we achieve that goal. The standard deviation and mean of the cold envelope is very similar to what we see in the full suite, and therefore represents much of the same information, using a suite that's some 70 or 80% smaller than the full ensemble. So I'll go through a little bit of a summary slide. We've ranked the models based on the process-based metrics performance in the PNW, and the culling thresholds are established based on the historical precipitation and temperature trends. And then projection envelopes of the cold ensemble have similar means and spreads compared to the full ensemble. And based on the historical trends, the cold historical envelope outperforms the full ensemble with respect to the observational data sets, which is, of course, by design, as precipitation and temperature trends are included in our metric suite. And then culling using this methodology reduces the ensemble size by 60 to 70% with virtually no loss in the historical trend uncertainty representation. And this methodology can be easily applied to any latitude and longitude box on the globe. So then I did a split sample analysis. You don't have to look too closely at this. But the idea is that if you consider only 1901 to 1950, and then use 1950 to 2014 as your targets, that's what we're showing here. And here are all the different metrics for the period 1901 to 1950. I mean, we still see in 1901 to 1950, the models are still a bit too cool and wet. Temperature trends closely match the observations, while now the precipitation trends are a little too wet. So the behavior and the other metrics are generally stable, and they're very similar to what we see in 1901 to 2014. And using split sample analysis, here's how the models rank compared to each other. Basically, as I said before, we find that there's very little change in the top performing models. The top 8 remain the top 8, and there's some slight shifts that I showed earlier in that spreadsheet before. And basically, these red models drop out of the culling threshold. These green models move into the culling threshold, but in general, the envelope is very stable. And so if we show split sample analysis culling effect on the historical trends, on the left here is the 1901 to 1950, where I've drawn the line at 10 models to minimize the error between the observations and the CMIP6 envelope. What effect that has on the 1951 to 2014 projected trends is shown here. We see that the full suite of CMIP6 models is the black dots, and the red dots are the cold envelope. We see a very similar effect, becomes slightly cooler, slightly wetter, which verifies fairly well in temperature with the CRU and UDEL data sets. It looks like culling does make it slightly wetter, but the projections of temperature, I mean, they're very close to 0. So, I mean, we're working with limited observations, so it is what it is. And so I have a few slides kind of previewing the global metrics. I haven't had the time to fully flesh these out yet, but it's just a little preview. Here's what the global metrics ranking looks like. It's the same metric suite, but applied around the entire globe, and including only the CRU, UDEL, and ERA5 data sets for verification, because those are the only ones with global coverage of the 6 observational suites I was looking at. So these results actually differ quite strongly from isolating the Pacific Northwest, which is not really a surprise. This analysis is also only considering land points, considering that the intent of this is to apply to hydrological applications. It would be interesting to see what sort of results you get if you look at oceanic points as well, which is something I intend to do. Many of the top performers we see here, though, are also top performers when you consider only the Pacific Northwest. Like NOR ESM2 was the top performer in the Pacific Northwest, and we also see CESM2 pop up in the top 10. The CAMS Chinese model is somewhere on there. Yeah, right here. And then the GFDL CM4 is a top performer as well. But again, there's considerable shifting outside of those top performers. So I think it's interesting that, at least some of the top performers we see in the Pacific Northwest also perform well globally, and it gives some sort of confirmation that the models that perform well are representing processes well on a global scale as well. And here's again that this is for the global suite. When you consider so many points, it's not too surprising that the spatial correlation and spatial standard deviation are well represented. But it's still a good sanity check to make sure that that's happening. And yeah. So just a little summary and some next steps. We've developed a framework for regional evaluation of ESM fidelity for hydrological applications. The relevance of the global metrics is likely dependent on the application, but considering this is generally for climate change impact studies, I envision something where you choose a particular region of interest for your particular application, and determine the set of models that you want to consider based on metrics performance in that region. And then, as a sanity check, making sure that the models you choose, the models that fall out of that culling criteria, also represent global processes realistically. And if they don't, maybe you drop them out, and maybe you don't. It depends on your application, but at least you'll have that information. I found that the split sample analysis cold model suite is very stable and very similar to the full model suite. The global metrics cold model suite is not yet determined, but I intend to perform that. But the top performing models generally included in the P&W cold suite also appear in the global metrics, such as the ones listed here. Yeah, so next steps include to flesh out the global metrics analysis, to address information redundancy, perhaps through a weighting scheme, and the evaluation of high impact metrics by emergent constraints, and then to investigate some of the features common to the similarly performing models, such as that plateauing effect that I talked about previously. I.e., do similarly performing models include similar physics, dicores, cumulus parameterizations, etc. And then I envision a GitHub repo where you can select or even define regions of interest and determine sub-select which metrics you might want to include for your own ESM evaluation, basically. The framework I've set up, you basically just input Latin lon for a box that you want to evaluate and just run it through the metric suite. So the idea is to put that on the GitHub repo that should be accessible to anyone. But that's still in the early stages. I still got to clean up a lot of my code and generalize it and that kind of thing. So yeah, so that's my presentation. Thank you.
Okay, so we are now going to open it up to questions. And again, if you're online, there's actually, I just looked at the YouTube page, a link where you can get direct access to our Slido page. So you can insert any questions that you might have for Nicholas into the Slido now. But are there any questions in the room? Okay, so we'll go, I'm going to go Pete, Christine, come to Isla, Dan, and then, yeah, okay.
Great talk, Nick. I really like the idea of process understanding by, why certain models are performing better than others. And one of the really interesting things was you're showing the NOR-ESM and CSM sort of swap positions, but the big difference between those two is the ocean model, right? So, NOR-ESM has like the NEMO model in it versus like having POP. Do you think these are atmospheric processes or oceanic processes, or you just think you're still going to start like going through and trying to fundamentally understand which parts of the models are performing for Northwest?
Right. So, the ultimate ranking is based on an aggregation of all those metrics that we looked at. And those are mostly representations of temperature and precipitation, which are basically impact level, not necessarily so much process level. But we do want to include things like oceanic heat content representation. And the only problem with that is the observations are, leave something to be desired. But there are observational data sets out there that we want to include in our metric suite. Yeah, so, the information is there. We have the performance of each individual metric. And so as I investigate commonalities between the models that are similarly performing, it'd be interesting to see on an individual metric level that could be used to determine, where the processes might be lacking or where they're similar, where they're different, that kind of thing. So, yeah.
Thanks, Nick. I can see how this framework is very useful. So my question is, it sounds like this framework can be done anywhere just by your Latin lombex. I'm assuming you've actually looked at different regions, and so I was just curious what other regions you've looked at, and in particular, like different climate. Like Pacific Northwest is a very wet climate compared to like a desert or something. And so, is there a difference in the different types of climate zones when you apply this metric?
That's a very good question. I actually haven't applied this framework to different lat-long boxes yet, but it's certainly something to look at. Because yeah, I can definitely imagine the performance varying depending on climate zone, absolutely. So yeah, that's definitely something to check out. I will note it right now. And I mean, in the eventual tools that we want to send out into the world, I would want some representational regions as kind of a pre-built thing to look at. So that's definitely something we want to do. Maybe, certainly around CONUS, we want to look at a few different regions. So, I mean, yeah, we want to make sure that the examples that we give are in some way representative of different climate zones.
And presumably that would give you a way to also assess the transferability of the approach that you've utilized here for other regions.
Thanks. So I can definitely see why you'd want to pick the models that are best in the present day, but you could imagine, like for climate change response, something totally unrelated actually dominating. So I'm wondering if you've thought about incorporating whether these metrics are actually linked to the climate change response, and if they're not, what is the motivation for culling based on them? If something else might dominate and another model that might not be good in the present day might do better in whatever is kind of dominating in the change.
Yeah, I mean, I think that's a fair concern. Obviously, we're assuming stationarity in this analysis by considering only the historical period as our culling criteria. I would guess the hope is that by using this split sample analysis, only using 1900 and 1950, to then see how that affects the 1950 to 2014 changes, in some way tries to get at that problem. But I mean, it's definitely an assumption that we use, and we don't necessarily address it directly. But I'd be curious to, know how we could do that. I mean, I'm sure there's information out there, but yeah, we do assume stationarity and use that.
If your ensemble spread in the future is reduced, I guess that's maybe one metric, and it seemed like it was. So there must be some link then between what you're
The spread was
basing it
actually
on.
largely unaffected in our
Oh,
future.
okay.
The idea was that we reduce the number of members, but in the end, the mean and standard deviation of the projected envelopes is largely unaffected.
Okay.
Hi. So this is annoyingly a question kind of related to Christine's. But so in terms of climate regimes, just I was thinking about the global metrics again, and I was going to ask how they performed for cold dry versus hot dry versus cold, so for example, within polar regions, they're going to behave quite similarly. It's not just defined by latitude, longitude, but those climate regimes might be able to be defined by those kind of quantiles. And then potentially in the future, for future scenarios, saying that if a model performs poorly in a specific regime now in this location, then when if it becomes that regime in the future, then it might have a similar bias. So being able to trace those kind of connections, I think, would be interesting.
That would be very interesting. Thank you for the idea.
Thanks for your talk. First, a clarifying question. So could you say again how you compute statistics over your two intervals? Does that include internal variability in the observations?
So all of the information I'm looking at is on a monthly time scale, and they're mostly like annual averages. So let me go back to the Sweet. Yeah, so for the split sample analysis, basically, I performed the exact same calculations, but only I isolated the 1901 to 1950 period. So for things like mean annual temperature, you just take an annual average and then average the annual average to get the mean annual average temperature. So
I guess just to say that there could be a component of good fortune for various models as to whether or not their internal variability might line up with that in the observations. And that might also depend on the ensemble size, I guess, whether or not you're doing averaging.
Yeah, so right, the ensemble size varies greatly between these different. Some models included only have one ensemble member, and others have up to, I think, like 70 is the largest ensemble we consider here. So that's a fair point. I guess the hope was that by considering 1901 to 1950, you average over a long enough period that most of that internal variability averages out. But obviously, there are some processes that occur over larger periods. So there's only so much you can do, I guess.
Okay, great. Thanks for that clarification. I also had another question, I guess, kind of getting to some of what's been asked. This task of forecasting future climate is a really challenging one, and the uncertainty quantification is a piece of that as well.
Mm-hmm.
I wonder if, in addition to ranking models, you'd considered providing maybe a mixture of these models, like a weighted sum of them that you might use for a forecast, and using varying weights to qualify uncertainty in the future.
Yeah, we certainly intend to do that. It's something we haven't done yet. But I will say that part of the goal of this study is to reduce the amount of data that you want like impact modelers or stakeholders to consider. So if you use a weighting scheme, you're still giving them a full suite of models to look at. And so if the idea is to inform downstream projects such as downscaling methods for hydrological applications, I think there's some advantage to reducing the model suite to a limited subset. Because things like downscaling and analysis of downscaled data sets is computationally expensive. And if you can reduce that suite, then you reduce the amount of computational power required to use those methods and apply those to hydrological models. So we do intend to do some investigation of weighting schemes, but it's also important to reduce the model suite as well. So there's give and take there.
Well, as always happens, Nick just made a point that I was about to ask him about, so kind of nullifies that part of the question or comment. But I do think, following up on what Isla said, there are kind of two objectives that emerge from this work, and one is the one you just mentioned, which is this kind of suite reduction, which facilitates like stakeholder impact studies without actually reducing future uncertainty. You kind of preserve like the change signal and uncertainty. But the other really hard objective was actually reducing the uncertainty through weighting models so that you have more confidence in their change projection. And that was the motivation actually for the original workshop that we had, that we invited people from, model developers from NCAR and other centers to come and comment on how they thought about that challenge. And I think what we found was it's really hard. As you suggested, there's some ideas out there like emergent constraints and things like that that maybe lead us in that direction. But I really feel like this is still out there in front of us. And I wonder, Nick, if there are other things that you plan to do before the end of the project to try to get at that, identifying models that project change better than other models, that part of the problem.
Yeah, it's a tough question. I would say that process-based metrics is a key to that. We want to do, comparative studies on stuff like oceanic heat content, which is an important question because models, they can cheat a little bit by hiding heat in the ocean. And when that doesn't have an impact on the metrics that we're looking at, which are all land-based, then there's some, I don't know, there's some misrepresentation of the, the real physical world that you're hiding. If you have an ocean that's very hot, but it doesn't tend to impact the processes. So yeah, I mean, things like that. I mean, just thinking about different metrics, different ways to evaluate processes represented in the model. And the idea, I mean, you'd want to select climate models that have the best representation of as many processes as you can think of. And thinking of ways to identify the relevant processes and being able to verify those in the observations is an important problem. And I think, the next step for these sorts of studies.
Yeah, so I mean, I think that process-based is really important. And I guess I don't come out of this like super convinced that you found a better set of models necessarily based on these metrics. And maybe there's ways to try to really tease that out by, identifying the metrics in here, which are really kind of capturing what Isla said, what would control or impact the response to climate change.
Right.
But in particular, I'm wondering about the use of the temperature and precipitation trends at all in this, because that's what you're trying to predict. And
Right.
and the historical temperature and precipitation trends that we've observed are just one possible realization, which have huge uncertainty around them. So I feel like the missing piece here is using the large ensembles to try to really figure out like what is the possible range of temperature and precipitation trends historically, because you're sort of culling the models to say we're taking the ones that best match the temperature and precipitation trends, but that's just one possible realization of it. So it's not a particularly convincing argument, I think, in the end. So I'm not sure where, how, in my head, I'm trying to think about how you do this, but I do feel like the large ensembles kind of need to be pulled into this to make this like more impactful.
Okay.
In some way. And Isla can probably come up with a better idea about how to do that than I can. I see your hand half raising.
I guess I was gonna say a similar thing. It's related to Dan's comment as well, that maybe what you could do with the large ensembles is a test of the uncertainty. So if you have a 40-member ensemble and you choose each member as your kind of equivalent to the observations, do you come up with a drastically different set of models that match those individual members best?
And I like the perfect model framework. Right?
Yeah.
We've talked about that. We just haven't done it yet, so it's definitely something we're considering.
And I guess also related, maybe, I mean, if you're going to be downscaling, I guess the temperature and precipitation could be more affected by the regional model itself, right? So maybe like the large scale circulation is more that you'd be driving those regional models with, is a thing to be paying attention to.
Yeah, no, I think that's fair. Yeah.
Okay, so Peter, you have another one?
So I guess I was just thinking, in terms of the reason why you're culling models out is because there's a one-to-one relationship between one of the large Earth system models and the dynamically downscaled forecast. Is that correct? So like if you've got an Earth system model, you're trying to work out, and you're doing the downscaling, is it dynamically downscaled or statistically downscaled? I guess is the first question.
The project that I'm working on is primarily focused on statistical downscaling methods, and determining their viability for this sort of impact study. So,
cool. Yeah. So I was just thinking about anomalies as opposed to when you're doing statistical downscaling as opposed to individual models. But you've kind of answered the question. If I was thinking if it was a dynamically downscaled process, then you obviously have to have forcing conditions, and that's going to line you up as to have a one-to-one relationship between the models, the Earth system model and the downscaling. But with statistical downscaling, I guess those relationships are very different.
Yeah.
Okay, are there any other questions from the room? So we haven't had anything come in on Slido. So if there are no remaining questions, I think we can thank Nick again for his presentation. Sorry. And with that, that concludes our 2022 seminars. And a reminder again, we'll have our first one on the 6th, but it'll be entirely virtual as the person will be calling in from San Francisco. Okay, thank you.
All right, thanks.